Okay, so thank you very much, Heather. I think everything should be in order here. So,
yes.
Okay, so again, sort of proceeding a bit more from Phil's talk, I'm going to talk about something that's really quite a bit different here as well. And I'm going to tell you something about the spaceflight experiments that we've had a chance to do and focus really sort of on the vascular and the cardiometabolic health consequences of those of the spaceflight that we saw in those experiments. So, is it just slow, or am I getting the same problem that Phil had?
I think perhaps it might be slow bandwidth. But
okay, I can control it with my mouse, fortunately. Okay, so spaceflight is really the ultimate sedentary lifestyle. Chris Hadfield is showing here the colors of the University of Waterloo when he was up in space. I'm going to use Chris as sort of my example here of what happens with people in space. Okay, so there are many things that happen in this really foreign environment. You have the effects of altered gravity, the habitat, of course, being a long way from Earth and isolation. Things like a modest increase in the ambient PCO2, which is something we've taken a quick look at. And then, of course, floating in space. There are some stressful periods of time when they do extravehicular activities, but I think you'll see pretty soon that there's a lot of floating. But first, a quick picture. This is the Soyuz launch vehicle. That's how people have been getting into space for the last 11 years. The capsule is in the upper right-hand corner there. And then I was able to get into a mock-up of it. So that's me sitting in the middle there next to a dummy and one empty seat. It used to take about 2.5 to 3 days to get to the space station, and that was the space you had to live. Fortunately, they've taken a different route up now, so it's only a few hours. And coming back is really the astronauts describe it as being a car crash. You land very heavily in Kazakhstan. The capsule that's in the upper right-hand corner there is Bob Thirsk's capsule. Bob, of course, was the first Canadian to spend 6 months on the International Space Station. You can see the charring there. It's really a very hostile environment when they're returning from space. The Americans, as I just suggested, have been going to space with the Russians. On the far left is one of the last shuttle launches. That little picture of the shuttle landing up above the reeds in Florida, we were actually able to be there for some landings and test some of the astronauts fairly soon after they got back from spaceflight. And on the right-hand side is the Dragon, SpaceX Dragon X capsule being launched. Supposedly next week, next Wednesday, is to be the first U.S. launch since 2011. Things almost always shift right with U.S.-based launches and landings, so we will see what happens. And these two guys down in the bottom left-hand corner will be the first two Americans to launch on SpaceX. Oops, sorry, just hit the wrong button. Oh, there we go. Okay, so floating, as I said, it's an environment that's unlike what we have here. You're totally unloaded, and this is Chris floating through the capsule, through the space station. You can see it takes absolutely no effort other than to catch yourself every now and then if you're going a bit too fast. But the body is totally unloaded by being in space. So the cardiac system is unloaded, the skeletal system, the muscular system are all unloaded by spaceflight. To get around that, they do some exercise. So this is Chris cycling. The cyclergometer on the space station is really kind of unique. There's no seat. There are a couple of grips that they can hold on to with their hands. Otherwise, it's just the pedals. So Chris is actually doing a couple of experiments here, and he's getting his blood pressure monitored, his temperature monitored. So this is the cycling exercise they can do every day, treadmill exercise that they can do sometimes. Chris actually describes this as trying to run in a canoe. So you can imagine, that you're held down by the belt that's around the waist and the shoulders, and you can't apply a heck of a lot of pressure. So they get up to about 0.7 times the normal impact force on Earth at maximum. They just can't load themselves any heavier than that with the treadmill. They also do resistance exercise, and this is the IREDI, the Advanced Resistance Exercise Device. It's a hydraulic system. It can be used for squats or deadlifts or a whole bunch of other exercises. It can be reconfigured in many ways. And this system actually allows them to load potentially up to 700 pounds. It's a really good system in the sense that you can apply great forces to the this musculoskeletal system. Is potentially a bad system because they're questioning whether or not the really elevated blood pressure that you get during that type of maneuver and then Valsalva maneuvers on top of that, they're questioning whether or not that's leading to some of the vision problems that astronauts are experiencing. So what I've got here are a couple of example days of exercise on the IREDI. So on the left-hand side, it's flight day 13. You can see they did a couple of sets of shoulder presses and a whole bunch of other exercises. I point out down near the bottom, they're squatting with about 220 pounds. On the right-hand side, you're now up to flight day 152, and you can see the squatting is now up to 325 pounds. So definitely they progressed during their time in space. They can, you can see some of the astronauts come back actually very well muscled in their upper body, at least. There are some questions about what happens in the lower body. Calf muscle is extremely difficult to train in space flight. But it's a big improvement over what they used to have. This is something called the Interim Resistive Exercise Device, or the IREDI. Inside those two cans just to his sides are some plastic sheets that rub together and cause friction. So needless to say, they weren't able to load themselves very well with that. During this period of time, they had very large bone loss as a consequence of unloading of the hip and the lower spine. So there was a lot of bone loss, and that's why they developed the IREDI to go beyond that. And just because it is a muscle conference, I put in a slide of the cross-sectional areas of some muscle fibers. And as you can see, it says that the slow fibers are 31.5% smaller in cross-sectional area. This is one of the old shuttle day experiments. These people were in space for 12 days, and the shuttle was really, really small, didn't have a lot of room for exercise devices. So the astronauts were really quite untrained when they came back from space flight. And food. This is a picture Chris took of some foods that he got out of the cupboard. You can see lots of dried things, so they rehydrate them and so on. But the most visible item on this whole slide, and Chris did this quite intentionally, is orangeade. Astronauts undereat while they're in space. They lose appetite a bit. Maybe it's something to do with how the food moves through the digestive system. But typically they underconsume. So they're told to take this orange sugar drink. Some of the astronauts say, but I never drink that stuff on Earth. Why would I do it in space? The only reason they do it in space is just simply to increase the total caloric content. and a little bit more food with Chris. And some of the other things that all of the astronauts do are research experiments. They take blood samples from themselves. They have mice on station, which could be put into the Melfi as well. And Chris also did some experiments for us, one of which was this experiment we call BP-REG. Just really quickly, we're measuring his blood pressure response to a drop in arterial pressure. So that CBPD points to a continuous blood pressure device that's on his finger. The LACS, leg arm cuff system, so he's got cuffs around the upper thighs. Those were inflated to above systolic blood pressure for 3 minutes. Rapid release of the cuffs, you get a drop in blood pressure, you get a cardiac response to that drop in blood pressure, and you see whether or not the baroreflex changes from pre-flight to post-flight. With Caitlin Wood, we've just published recently that the answer is no, it didn't. So unfortunately, this is fairly nice way of testing the acute baroreflex. Doesn't really point out who's going to be most susceptible to fainting post-flight. So that sort of brings me to the vascular series of experiments that we've been doing on ISS. The first one, called Vascular, looked at the cardiovascular health consequences of long-duration spaceflight. I'll show you some of the data from it in just a couple seconds. Vascular Echo, we now have hopefully our last astronaut back on the ground, as long as we continue to successfully collect data from her. She will be the last one. The vascular aging experiment, our first astronaut landed not too long ago. Our second one will be launching relatively soon. And another experiment that's called vascular calcium is still in planning, but I'll show you a tiny bit about it a little later on. So why are we concerned about spaceflight relative to health? Well, part of the answer comes from our knowledge that's been gained over the last 20 years or so about how important physical activity is to our cardiometabolic health. Prolonged sedentary time is associated with development of insulin resistance and increasing inflammatory biomarkers. So one of the first things that we did in an experiment some years ago was actually quantify how active people were in space. So on the right-hand side, Mike Fink is showing off the gear that we hooked him up with to assess activity and heart rate. So he has the black straps on his wrist and ankle are activity monitors, and he has a Holter monitor for recording a 12-lead ECG. So from that, then we're able to look at what the heart rate response is relative to the ankle activity response. And so what you see over here is pretty well every time on Earth when you get a burst in ankle activity, you can get a corresponding burst in cardiac activity. So the heart rate goes up. And especially if the person goes for a run, you get a definite increase in ankle activity and heart rate. In space, notice that there are very few bursts of activity because, as you saw with the video of Chris floating through the space station, the ankles just sort of follow behind. If they do IREDI type exercise, you get bursts in heart rate, not a lot of ankle activity. If they go on the cycle ergometer, and you get a bigger increase in heart rate. But this is definitely a sedentary lifestyle in between those periods of exercise. But one of the things that astronauts love to say, and I had Chris come and do a talk to my undergrad class, and he said, well, we exercise for 2.5 hours per day. Astronauts do not exercise for 2.5 hours per day. We looked at the activity records, the exercise records for these astronauts. One of these M people down here is in fact Chris, and you can see that he on average did not get more than 24 minutes per day of aerobic exercise. They do cycling, they do treadmill, and they do resistance exercise. Usually, most of them are averaging about 5 or so sessions per week of resistance exercise. But this really is a sedentary lifestyle. They spend 21 to 22 hours per day just simply floating. So one of the consequences of this, of course, is that they're going to lose fitness. And so these are some data taken from Alan Moore, who investigated the VO2 peak during spaceflight and in recovery. And what's shown on here is this drop from the pre-value to early in flight. This is the average line going up here of what their VO2 peak is. You can see it is recovering during space flight, but doesn't really get back to the baseline. Now, this is the average. There are some individuals who are able to get back up to and perhaps even slightly above, but it really depends on their values. So if they are fit before they start, then they tend to drop. If they're less fit before they start, they tend to go up. So here we have then the increases in the VO2 post-flight, and by a month, they're getting pretty close to back to normal. We've done an experiment trying to look at what happens to muscle blood flow in the legs. So we get them to do these plantar flexion types of exercises with an elastic band. Hidden in behind this white and black strap is an ultrasound probe. We've measured the recovery blood flow after they've done a minute of exercise, and we've looked at the time constant, how quickly they recover. For this one person, it looks like it's slower immediately post space flight. 4 days after, looks like they're slower. But on average, across all of the astronauts, it's not really showing us too much change. Okay, so why do they exercise only 30 minutes per day? Well, this CVIS up here is that cycle on the vibration isolation system, and T2 treadmill over here. These sessions are 60 minutes long, but that includes the time to get changed before their exercise, their time to set up the device, time to exercise, time to clean up, and then get back onto their next activity on their schedule. So that's why they can fit in only 30 minutes per day of aerobic exercise. Now, we looked at the insulin resistance consequences of this. So these are fasting blood samples, pre-flight and in-flight. The solid lines are men, the dashed lines are women. And you notice that all of the astronauts have an increase in-flight of their fasting insulin concentration. And the HOMA-IR calculated from the insulin and glucose, all of the astronauts increased. And you can see there are a couple of them who are starting to get up, to a level that you might not want in a healthy astronaut. One of the things that we also looked at was glycated albumin. Because of the turnover of the HbA1c, we went to a shorter turnover molecule, albumin, and we're seeing some trends here for increased glycation taking place. So fasting blood glucose, though, is not an ideal way of looking at insulin resistance. These are some data from our colleague Martina here during bed rest. So baseline, the blue line shows an increase in glucose following an oral ingestion of 75 grams of glucose. After 21 days of bed rest, you get a much bigger increase and is a much prolonged elevation of that glucose level. This, of course, is potentially going to lead to increased glycation products. So we have fairly recently completed the first ever oral glucose tolerance test on the space station. Luca Parmitano here is consuming his 75 grams of glucose. We did some blood sampling as well as some finger pricks. And unfortunately, I can't tell you very much about it. I can tell you, though, that Luca's very open about being an astronaut who follows a ketogenic diet. So he's not your typical astronaut. And so we're really interested to wait and see at the end whether or not he stands out as being sort of the odd person in terms of the responses. So the other thing that we've been looking at is what happens to the arteries with spaceflight. We initially thought, well, it's, once you get rid of the hydrostatic effect. So you can see as you're all upright, I assume right now, your blood pressure in the head is 70 millimeters of mercury, which is about 30 less than it is at heart level. If you were going to space, your blood pressure would be the same in the heart and the head, all 100-ish. So that might cause an increase in the thickness of the arteries in the head, but you'd expect then a decrease in the lower limbs. You, of course, have changes in physical activity, hormonal balance, and the cardiometabolic status we talked about, and perhaps vascular calcification too. So animal models, the hind limb suspension model has been widely used as a way to try to simulate some of the effects of spaceflight. So here are two different labs in which you can see that from before suspension to after suspension, you get an increase in the thickness of the middle cerebral artery, just simply, primarily as a consequence of that elevated blood pressure. So what we've done is to measure carotid artery dimensions by ultrasound and carotid artery pressures by a tonometer, and take those and calculate the distensibility coefficient. So let me just focus on the right-hand side here for a second. This is the normal population, so over 1,000 people here in this age group going from 45 up to 85, and you see an arterial stiffness with aging. Our astronauts, the women and the men, pre-flight and post-flight shown with the stars. You can see there's sort of a 10 to 20 years increase in stiffness indicator with just 6 months in spaceflight. The other thing that happens is the walls get thicker, the intermediate thickness increases. So you've got then the this thicker wall here that's also occurring in the lower leg. So that's really kind of interesting. So I'm going to skip ahead a couple of slides because I want to show you one new development here. And this is using the radio frequency signal from the ultrasound to actually detect the reflection off these bright walls. These are pre-flight values here. These are post-flight. So these are data that we're just writing up at the moment, showing us that we do in fact get an increased arterial stiffness or stiffness indicator from this ultrasound measurement. Okay. And so thanks, of course, to all of our astronauts who have taken part in our studies over the years, and thanks to my colleagues around the world who have all contributed to this as well. And I see Heather there waiting to
Thanks.
Finish.
I'm just giving you your 3-minute warning, I guess, for questions. If there are any questions, feel free to write them in the question and answer section. One question that I had, it was very interesting that the astronauts think they're exercising for 2 hours, but actually only 20 minutes. Do you think that's true of people on Earth too? Do we all overestimate what we're actually doing?
Probably, because most people likely include the time when they're just getting to the gym and getting changed and so on. So they probably overestimated a bit. I think most people now, though, are starting to use some sort of device to track them, or many people are. At least the ones who are interested are doing that. So I'm sure it's coming closer to what they're actually doing.
Heather, I have a question, please. This is Haas. How you doing, Richard? Nice job. I was in part of the Ball State group for a number of years through my PhD, and I worked on the ULLS study out of Arkansas and the 90-day bed rest study, and then the 60-day bed rest study out of Toulouse. And we used the inertial ergometer, right? Remember that thing?
Mm-hmm.
What happened with that? That seemed like it made a lot of sense in terms of going onto the shuttle and onto the space station in terms of just bulk and physics. It never matriculated. And similarly, Alan's lower body negative pressure unit, I mean, that showed remarkable results in terms of preserving cardiovascular function. That never matriculated either. So what can you say about those things?
Yeah, Alan's device, as you probably saw it, was huge. And, so you just don't have room for it or the ability to launch it. He and his colleagues have been working on a much smaller portable device. I think it's coming closer to being launched. The concept here is that you create a negative pressure in the lower part of the body, which causes a cardiovascular gradient, but then it also increases the impact force as you are running inside the device or, just doing any kind of exercise. It makes it more Earth-like. So definitely you need to, you need to try to simulate gravity as much as you can, but you have to do it economically because there just isn't the ability to, to launch anything that's very big. The centrifuge has been really big in terms of research lately, but I don't know how you're ever going to get a centrifuge in space.
What about the inertial ergometer with, the muscle preservation? That was the yo-yo device by Per Tesch.
Yeah, Per Tesch's device. Well, again, it's fairly big and bulky. It's got a huge flywheel on it. So it's, yeah. I mean, you can do that. Well, you're able to do that right now with the ARED. You can, in fact, attach, make it essentially into a rowing machine. So that's it. In terms of the musculoskeletal part, ARED is able to answer most of the questions. They're now seeing very little bone loss, especially when ARED is combined with bisphosphonates. Not everyone wants to take bisphosphonates. So the musculoskeletal part of it with the ARED, most of that has been met. So I might not need Per Tesch's yo-yo any longer.
Thanks.
Does Dave have a question, or can I read one of the ones online?
Oh, go to the ones online, please. Sure.
First off does radiation have a role in the arterial stiffness seen with spaceflight? Should we be including radiation in ground-based models?
Let me just back up a slide or two here. So the answer is potentially yes. It doesn't look like low Earth orbit radiation has an impact. We're not detecting endothelial dysfunction the way it was hypothesized. But once you get beyond low Earth orbit, which is supposed to happen in a few years, absolutely, because the galactic cosmic radiation has a huge impact in terms of causing an oxidative stress and endothelial dysfunction. So absolutely, radiation-induced cardiovascular disease is going to be something that has to be watched very closely.
And I think we'll just do one last question online, which is, Do you think that a consistent hypercaloric diet in conjunction with meeting the recommended physical activity guidelines would be enough to significantly mitigate the changes to cross-sectional area seen after flight?
In terms of the muscular response, probably yes. You're just going to have to make sure that your exercises are balanced and come as close as possible to loading, what you see on Earth. I commented on the calf muscle being extremely difficult to maintain with space flight. Even people who do a lot of treadmill running, it's very challenging for them to maintain the calf muscle cross-sectional areas.